In this video, I want to show you how to determine the direction of current due to electromagnetic induction. The first thing I want to do is I want to review the notion of a loop. Okay, if we've got a loop of wire, like for example this one here, okay, there's a rule for the direction of the flux inside the loop. Now, what's really going on here is that the magnetic field is actually, since it's going this way, right? I'm using one of the right-hand rules, my thumb in the direction of the current. The magnetic field lines are actually coming on the inside of that loop, coming out of the page. Okay, no matter where I go, it's out of the page, inside the loop, and then of course outside the loop, it's into the page. Okay, but an easier way to do that is to just simply put your fingers in the direction of the fields, or the current, right? So the current's going anti-clockwise, right? My thumb is the direction of the flux inside that loop. It's out of the page in this case, or toward you. Okay, so let's look at another one here. Okay, well this one is the other way, so I've got to take my hand and do that way. Now my thumb is into the page. The flux would be into the page. Okay. Okay, so now the current is going up the front of the coil, right? So I have to go like this, up the front of the coil. The north pole is to the left side there. Okay, or that's the way the flux is inside the loop, right? If the current's going to the right, then inside the loop the flux would be up the page here. It would be that way. If the current, going down the front of the coil, I got to go around. Okay, if it's going that way, if it's going down the front, then the flux is going this way inside the loop. Now let's see. Current's going to the left, so the flux would be down, or the north pole would also be down, right? Okay, so now let's do the direction of the current. And the rule for this, there's two rules, or maybe there's three rules. Okay, the rule is that if you gain something, you oppose it, because you always resist the change in flux. And if you lose something, you replace it. So in this case, this red square here is leaving that area where there's flux out of the page. So in this case, we're losing flux out of the page. And so what we do is we replace that. Okay, so as this thing is being pulled out of the page, and only when it's moving, by the way, okay, the current is going to flow anti-clockwise on here. Okay, it's going to flow that way to create the flux out of the page, right? It's losing flux out of the page, so it replaces the flux out of the page, right? Now, here's this thing, right? It's getting pushed, and pretty soon that thing's going to be in this place where there's flux out of the page. It doesn't like that, right? So it's gaining flux out of the page. This one's going to oppose that, right? If you gain flux, you oppose the change, right? So in this case, we're gaining flux out of the page. We oppose that by going clockwise. Okay, my fingers go clockwise. That creates flux into this page. Okay? Okay, so this thing's not even moving. We just have the magnetic field. Somehow we can change it, and the magnetic field increases, right? So we are gaining flux into the page. If you gain it, you oppose it. So we would create flux out of the page. Okay, so the current would flow anti-clockwise here. Okay? All right, again, in this case, it's the same exact thing. We're gaining it not by the magnetic field increasing, but we're putting it from where there's no magnetic field to where there is, right? So we gain flux into the page, we create flux out of the page. The current, as it's being pushed in there, it'll flow out of the page, or it'll flow anti-clockwise to create flux out of the page. Okay. Now, keep in mind, it only flows while the flux is changing. Once you get it into the magnetic field, you can move it around in here as long as this is a uniform magnetic field and you don't rotate the wire. There won't be any change in flux, so there won't be any current. Unless it's a superconductor, in which case it would be flowing because you started it flowing. Okay, so this is either we're rotating the loop to create this effect, or we're smashing the loop, right, somehow, right? The net effect, though, is that we lose flux into the page. Right? Well, if we lose it, we replace it. So in this case, we would create flux into the page. It would go clockwise. Okay? Now, for this type of thing here, what you want to do is you actually want to talk about the resisting the motion of this magnet. Okay? So for this thing here, we're going to pretend that that's a coil, right? And we've got this magnet going away from us, right? Okay? So I like to think of these in terms of resisting the motion of the magnet, right? So in order to keep that north pole from going away, we want to create a south pole on this side of the coil, right? That's going to be a south pole. To do that, if you recall, you make the current flow up the front of the coil. So that this is the North Pole, that's the South Pole. Okay? And then here, for this guy here, you've got the South Pole getting pushed into this coil here, right? We don't like that. We don't want the South Pole to enter this vicinity here, right? So the way we repel it is we make a South Pole toward that guy, right? And so the way to do that is have the current flow down the front of the coil to make this the South Pole. This is the South Pole side of my hand. This is the North Pole, right? Okay, let's do another one here. Okay, now the South Pole, it's been here for a while. We don't want it to go away, right? So if the South Pole is going away, how do we keep it around? Well, we make this a North Pole, right? So the current's going to go up the front of that coil and make this a North Pole, and it'll attract it, okay? And of course, the reason for all this is that this is something called Lenz's law that states that the change in the current that flows resists or goes counter to the change in flux, right? But it basically boils down to conservation of energy. If you're getting electrical energy here, you have to be doing work there to create it. So it has to be opposing your motion. Okay, so this thing here, what we're supposed to interpret this is that this stays fixed. This little U-shaped thing stays fixed, and this thing slides that way, right? So in this case, we're losing flux into the page, right? Because this area is getting smaller. It'll be here, right? And if we lose into the page, we replace into the page. So it's going to go clockwise, okay? Now, by the way, you can simply go, if you're a positive charge on here, you can say positive charge on this wire that's moving goes that way. The magnetic field is into the page. I'm just using my right-hand rule. Current will flow down this stretch, therefore go clockwise on this coil. You can do it that way too. Okay, this is my favorite one, right? Do you want to be stuffed between the poles of that magnet? Heck no! Right, so to resist that, right, what's going to happen is the current's going to flow in such a way that there's a North Pole against that North Pole, South Pole against that one. So it'll go to the right on the front of the coil. Oh, you got to love this one. Holy right-hand rules, Batman. So the magnetic field, due to this wire, is into the page there. It's a bunch of X's, right? Okay. We are increasing into the page, right? Because due to this wire, thumb in the direction of the current, fingers in the direction, right? Due to that thing, we have into the page. Since it's increasing, we're increasing into the page, right? And so in this case, we resist that by making out of the page. This loop is going to have out of the page flux and therefore go anti-clockwise. Okay, now the current is decreasing, so we're losing into the page. Well, if we lose into the page, we replace it by going clockwise. This loop here is going to have clockwise. Okay, and then this one in the outer loop, right, the flux inside there is decreasing. So we're losing out of the page, right? Well, if we lose out of the page, we replace it. So the inner loop there, the red loop, is going to have anti-clockwise current to create flux out of the page. Okay, this is fun. The resistance is decreasing. Now, at concept 0, the current is actually flowing anti-clockwise. It goes from the big side to the small side, right? Okay? If the resistance decreases, the current increases. So we are creating flux out of the page by this current, right? And that current is increasing, so therefore the flux is increasing. So we're increasing out of the page. If we increase out of the page, we oppose it. If we gain out of the page, we oppose it by creating into the page. All right. Woo-hoo.